The preceding lecture covered the statistics used to describe the results from a sample. In this lecture, I'm going to cover the statistics used to assess specific questions that can be framed as hypotheses. Most of these hypotheses are about differences between groups or differences between conditions. The first set of statistics involve one variable and are therefore called univariate analyses. Let's start by clarifying what we mean by hypotheses. Hypotheses are formally expressed in pairs. A null hypothesis, which is symbolized as H sub 0, means there's no effect, there's no difference. And the alternative hypothesis, typically symbolizes H sub 1, is yes, there is a difference, there is some effect. That may be a directional effect. It may be that one group should score higher than another group, or one condition should be better than another condition, or it may simply be that they're not equal. A second consideration in hypothesis testing is the significance level. We've referred to this before using the term certainty. Significance level is the formal term. It's often expressed as a p-value or an alpha level. So those are synonyms, or a significance level. And this is a decision that's made by the researcher prior to conducting the research. How much confidence does the researcher want to have that the results are capturing a true effect? There is a strong tradition in social research to use 0.05 as the significance level, which means that the researcher is 95% confident that any result that exceeds the critical value is a true effect. But two other common ones are 0.01, which would imply a 99% confidence level, and 0.10, which would imply a 90% confidence level. So those are referred to as the critical alphas, or the critical statistic required. And what we will be doing is using the sample data to calculate an observed level. So there's a p critical and then there's a p observed, and that's determined by the z or the t-score that results from the sample data. So let's take the simplest hypothesis to test, which is a sample mean versus a point estimate. A very common hypothesis here is that the mean is different from 0. So a sample would be measured, and the average for that sample would be computed, and then it would be compared to 0 to see whether it's significantly different from 0. Now these comparisons can be either one or two-tailed tests, and that whether it's one or two-tailed affects the critical value that's used in the test. When it's a two-tailed, it is a two-tailed test when the hypothesis takes the form of equality. That is, the hypothesis is that x bar is equal to mu. So if you're testing the null hypothesis that x bar equals 0, then deviations either above 0 or below 0 would be of interest because they would contradict the null hypothesis. And you would use a one-tailed test. I'm sorry, so you would use a two-tailed test. A way to think of this is that the alpha level, say the typical 0.05, is apportioned equally on both sides of the distribution. So with a 5% tolerable error, you would be apportioning 2.5% on the two high scores and 2.5% on the two low scores. So if you're testing that x bar is equal to mu, you need to have that 2.5% on either side. But if your hypothesis takes the form of greater or less than, so you're testing not that x bar equals mu, but simply that x bar is greater than mu, so you're testing the hypothesis that the sample mean is greater than 0, for example, then you're not concerned about any error on the low side. So you can take your entire 5% on one side, and since the critical values in tables are always listed with equal parts of the error on both sides, you could look up the critical value for 0.025 rather than 0.05. And that means you'll have a lower critical value to surpass. And it's important to keep that in mind. Now, the t-test statistic, which is called the t observed, because this is the t that you're observing in your sample, is computed as the difference between x bar and mu. Mu now is your point estimate. So your hypothesis is the form of, I think that the population mean is whatever. And that's what mu is. I think the population mean is 0, or I think the population mean is 5.2. And x bar is your sample mean. So the t-test is the difference between those two, x bar minus mu, divided by the standard error of the mean. So that's s over the square root of n. So the numerator is the difference between what you observed in the sample and what you hypothesized, mu, and the denominator is s, the standard deviation of the sample, divided by the square root of n, the size of the sample. That expression can be rearranged to create the confidence interval, and we've seen this equation before. So the confidence interval about the mean is x bar plus or minus the t critical value times the standard error of the mean. So that t critical value is a function of how confident you want to be. And you can look that up in tables. So you could look up t critical, and at a sample size of 20, what you'll see is that for alpha 0.10, t critical is 1.73. For 0.05, it's 2.09. And for 0.01, it's 2.85. And those are the two-tailed values. So that's the statistic for looking at a mean. What if we're looking at ordinal or categorical data? Then the question is goodness of fit. Does the distribution in a sample differ from what is expected? So this is a hypothesis about the distribution of values from one variable. And is that distribution different from expectations? So it's the same logic as the previous one. Remember, with means, we are raising the hypothesis that the observed mean is different from what was expected, and what was expected was mu, the mean of the population. So here we're asking the same question about the distribution of values across categories. Now, what is that expected distribution? Well, just as we could use a mean of 0 as the expected mean of the population, we often use an equal distribution across categories as the null distribution. So if we're looking at two categories, we might be testing to see whether the sample differed from a 50-50 split. If we had three categories, we would be looking to see if it differed from a 33.3, 33.3, 33.3 split. That expected distribution could also be something else. It might be, for example, the same distribution that we saw in the previous study or in a previous year. And we'll see some examples of that in the problems that we look at. So the appropriate statistical test for this is chi-squared. And chi-squared is calculated as shown here. The chi-squared observed is equal to the sum of the observed frequency minus the expected frequency in a cell. That quantity squared divided by the expected frequency in that cell. And chi-squared is distributed over different numbers of freedom depending on the number of categories. So the degrees of freedom is k minus 1, where k is the number of categories. So if you were looking at two categories, then you'd have 2 minus 1, 1 degree of freedom. If you had three categories, it'd be 3 minus 1, 2 degrees of freedom. So when you look in the look up the chi-squared values, critical values in a table, you'll see that there are different columns for different numbers of degrees of freedom, or different rows for different numbers, differing degrees of freedom. Another type of hypothesis that sort of bridges the two that we've looked at, means and distributions, is a sample proportion. So for example, a distribution that has only two categories, then clearly one of the categories is going to represent a proportion of responses in that category. And sometimes the hypotheses are stated that way. So the hypothesis would be about a proportion in the population, and H1 would be that P, the sample proportion, differs from pi, the population proportion. So it's similar to chi-squared, but it can be conducted with a t-test. And the reason that one can use a t-test when looking at proportions is that rather than counting the number of responses in the category, which is what chi-squared does, what you're doing is converting those numbers to percentages, and percentages form a ratio scale with equal intervals between them. And that allows one to use the t-test, which is a slightly more powerful statistical analysis. The t-test can't be used if we have more than two levels. So if we were looking at color choice among 4 brands, for example, we'd have to use the chi-square and look at the entire distribution across the 4. But if we only have 2, then we can calculate a t-test statistic, and that statistic looks very much like the statistic for the means. Recall that was x bar minus mu in the numerator. Here we have p, the sample proportion, minus pi, the null hypothesis proportion. And that's divided by the standard error of the mean, which is the square root of pq divided by n. Remember that p is the sample proportion and q is 1 minus p. So if we observe that 70% of the people were satisfied with the service, then q would be 30%, 1 minus p. And n, of course, is the sample size. All right, let me put what I've said so far into context for conducting univariate analyses. The first step is to determine the nature of the problem. Identify the question that's being asked, the hypothesis, and the level of measurement that was done with the sample. From that, one can identify the appropriate statistical test. So if the level of measurement was interval or ratio, then the test could be a t-test. If the level of measurement were categorical or nominal, then the statistical test would have to be chi-square. And if it was a comparison across more than one category, then it would have to be chi-square and not a proportions test. Then you find the appropriate equation, and this presumes that one is doing the analysis by hand, which one is almost never doing. If one is doing it with a statistical analysis package, this simply means clicking the right button from the menu. And you plug in the numbers and do the math, or you have the statistical analysis program do its magic. And then you interpret the statistical test, and you do that by comparing the observed statistical test value with the critical value. And the critical value comes from tabled values. So the critical value represents the size of the deviation that is just at the 0.01 or 0.05 or 0.10 level of tolerance for error. And then one draws a conclusion about whether the sample evidence supports the alternative hypothesis or does not.